Okay, so the meeting has started recording. So I'm going to put up this share screen here. All right. Okay, so we continue with the lecture notes. Right. So from here onward, you would not be tested in the midterm exam, right? So the Dirac delta function, you wouldn't be tested in the midterm on this. However, you could be tested on it in the final exam, which is, I think, most likely on the 18th, right? So we set the date for the midterm. The midterm is the 8th, Friday the 8th, which is 2 weeks from today, 1 to 3. So it will open in my e-learning, and you will go in there and you will do it, right? Right. Most likely it would be around the same 2 hours. So your time will count down. You will have 1 attempt to submit your answers and so on and complete the assessment, right? So let's begin. The Dirac delta function, right? So this is how the function is represented, delta into t minus t naught, right? So this kind of give you an indication similar to how the Heaviside function, the notation for the Heaviside function, yeah, h t minus t naught. However, this is a different type of function then, right? It's actually really not a function. We just representing it in terms of a function, right? It's used to represent an instantaneous unit impulse that occurs at time t minus t naught. T equal to t naught rather, not t minus t naught. So the Dirac delta function, delta t minus t naught, is not actually a function, as I just said. It is really a distribution. The theory of distributions belong to a branch of mathematics called functional analysis, right? So this is just a representation, a symbolic representation of the Dirac delta distribution, right? So you have your coordinate axis here, your t-axis and your Dirac delta t minus t naught, right? And you have here your t naught. This is your instantaneous time here along the t-axis, and you have an impulse like a vertical jump there, right? We give an intuitive description of the delta Dirac function as a limit of pulse functions, right? Consider a sequence of pulse functions, right? So this is a sequence of pulse function. So you notice here you define this in a piecewise manner, right? FNT, right? So n is your number of functions here that make up your piecewise function. So it's defined to be n, right? When t is between t naught and t naught plus 1 over n and 0 otherwise, right? So basically, the function is 0, right? Think about it, right? So if I draw my coordinate axis here, right? Let me just show you. So this is your t-axis here, right? So when you go along the t-axis, basically, so your function is 0. So which means your function is a straight horizontal line, right? Your function only becomes n, right, between t naught, right, and this, let me say this here is t naught plus 1 over n. Right, so let me just indicate it here. So between t naught here and T naught plus 1 over n. So which means this distance here, right? This distance between T naught and T naught plus 1 over n is actually 1 over n, right? And between here, the function is defined to be n. So on this axis here, that is your y-axis, or rather your, right, your Fn t-axis, right? So your function will be n, so it will be, right? So that is your impulse there, right? So between here and here, the function like it jump up, then it jumping up, right? Up and down, and it moving horizontally as that happening. So it basically forming a triangle then. You see the triangle, not a triangle, a rectangle, right? So I just drawing the rectangle here for you to see it. And then after here, it going back to 0 again, right? So that is your unit impulse, right? Now, if you look at the area of this triangle, this rectangle rather, right? So this will be the length and the width is that. So length by width will give you what? N by 1 over n is actually 1. So this area here is 1. Right? So look at some diagrams here showing the same idea. Right? So you see your T naught here is 0 otherwise, and between T naught and T naught plus 1, so that means the width here is 1, right? The jump is 1. Because if the width is n, right, the jump is, sorry, if the width is 1 over n, right? So 1 over n, and this here is n. 1 over 1, right, is 1. So n is 1. And look at this here, the second one here. This is a half. The width is a half. So the time between T naught and T naught plus a half, right, is a half. And then the height here is 2. Because 1 over n, 1 over 2, and n is 2. So you see 2 by a half is 1, right? 1 by 1 is 1. And look at here with 1/3, the same thing happening. So you're seeing here, note that the area under the graph of each of these pulses, right, of the function fnt is 1. As the parameter gets larger, the pulse, right, gets narrower and higher, because you're seeing that happening here. So as n increases, so that means your height getting, the graph getting taller. But what happening in the distance between T and T naught plus 1 over n getting smaller, so you're getting narrower, right? So I wonder what would happen when this limit here of the time between T naught and T naught plus 1 over n approaches 0. What will happen to the height? It will approach infinity, right? Intuitively then, you know? Right? So as the parameter n gets higher or larger, the pulse gets narrower and higher. Intuitively, as n approaches infinity, the function fnt tend to the Dirac delta function, right? Which is denoted by delta t minus t naught. That if it was to exist as a function, would take the form of a pulse with 0 width, infinite height, and area of 0, right? So think about that. If the width approaches 0, the height approaches infinity, but the area had to remain constant, the area had to be 1, right? But this height is infinite, so this is like a vertical jump that going on infinitely, right? So here again, we have the general function here, right? As the sum of Heaviside step functions, and hence determined. So you want to express the general function here as the sum of Heaviside step functions, and hence determine the Laplace of Fn t. And we know how to do this, right? Remember, this is the first interval here. So here, what we do here, right? Just before the function approaches t0, so you break it up into regions. So look, I have it here written, right? So I put some additional information here to guide you. So I write it, the function t between 0 and t0. And of course, before the function reach t, as I show you, t0. So all along here, the function before it reach t0 here is 0, right? So from 0 to t0, the function is 0, right? So that is why I'm breaking it up here like that. And then between t0 and t0 plus 1 over n, the function is defined to be n. And then beyond that, right, as was seen here, right, beyond that, beyond t0 plus 1 over n, the function again goes to 0, right? So you see, break it up in 3 parts, right? So from t0 plus 1 over n, right, and beyond, so t is between t0 plus 1 over n and infinity, right? So we break it up into 3 functions. We call them f1t, f2t, and f3t respectively, right? So we know the first one on top here, right? The first one here, you have to take 1 minus the Heaviside, t minus t0, and multiply by the first function. Then the second one, now you have to take the Heaviside, t minus t0, that is the first endpoint, minus the Heaviside, t minus t0 plus 1 over n. So you're minusing all of that, that is the next endpoint. And then you multiply that by the second function, right? And then the third Heaviside combination here will involve the Heaviside t minus t0 plus 1 over n, right? And then you're multiplying that by the third function, which is f3t, right? So when you do that here now, of course, you're going to see what's happening, because this here is 0, so this will drop out. So this part will drop out, right? The third part is also 0, so this part here will drop out, right? And just the part in the middle will survive, right? So what you will have here now, you replace this by n, right? Because f2t is n. So you'll have to multiply n by h at t minus t0 minus h at t minus t0 plus 1 over n. And then you take the Laplace transform throughout, right? So you take the Laplace of f of n t is equal to n by the Laplace of h at t minus t0, and we know this, and we also know this here. So this is the Laplace of a strict Heaviside function, which is e to the minus s t0 over s, and this one here is e to the minus s, this value here, t0 plus 1 over n over s, and you have to multiply it by n, right? So if you notice here, you could use e to the minus s t0 as a common factor. You could pull that out, right? And then you have n inside, and then you have in bracket 1 minus e to the minus s over n, right? Using the laws of indices, we would have to add back here. So you'll get back this value here, right? That was extracted over s, right? So that is a very important result here. The Laplace transform, so this is the theorem here of the Dirac delta function. Delta t minus t0 is given to be Laplace of the Dirac delta function is e to the minus s t0, right? So that is the Laplace of the Dirac delta function. So look at it carefully there. So this here is just a proof of it, right? So we have, it may be shown that the limit of n approaching infinity, fnt is equal to the Dirac delta function. So as this limit approaches infinity, we get the delta Dirac function in the same sense of distributions, right? So you could get this, you could look at the, this page here in this course notes, Math 2230, right? I think you may have access to that, so you would be able to look at it a little more in detail. Right, then we may define the Laplace of the delta Dirac function, right? So this could be found on this page here if you do some investigation, right? In this text here, it's written is equal to the limit of the Laplace of fnt, right? And we know that fnt, as we just discovered a couple pages above, look at here, right? This is given by this. So don't forget our result. Right? So that's the only thing we take in here is the limit. Now, remember, n approaching infinity. So this e to the minus st naught has nothing to do with n. So we could take that on the outside, and then we could take the limit of 1 minus e to the minus e to the minus s over n divided by s over n. So that is just this here, this part here. Because remember, when we divide by a fraction, right, it's the same as we invert the divisor and multiply. So this is the same as this up here. Because when you invert the divisor, you'll have to put the n here over the s and multiply. So you'll get back this here. So this is the way to write it here to see what's happening, right? And now we take e to the minus s over n, right? So the expansion here of e to the x is 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial and so on, right? So if I take e to the minus s over n, the first term will be 1. So basically, right, you're replacing your x with minus s over n. So this will be plus minus s over n, right? So all you have to do is take your time here and work through it slowly to make sure you understand it, right? And then you add minus s over n squared over 2 factorial, right? And then you the same thing, you continue going up to 3 terms, just for you to see the pattern. Minus s over n cubed over 3 factorial, right? So, and then now, notice you have a negative here, so this will be negative. Then you have a negative squared, so this will be positive. And then you have a negative cube, so this goes. So the terms will alternate in signs. So you see what happening here, right? Now remember, you have to minus 1 minus everything in here. So if you notice here, this 1 and this 1 here will cancel each other, right? So what you'll end up with in the numerator position is just s over n, right? That is this first term here, right? Because this will cancel out here, right? 1 minus 1 will cancel, and then a minus minus is a plus. So you'll get S over N, and then this will be plus, so then the negative here will give it a negative. So that will be minus S squared over 2N squared, and then the third term here will be a negative, but a negative will make it a positive. So that will be S cubed over 3 factorial is 6N cubed. And then you have to divide all that by S over N, right? So notice here, the S over N will cancel with this S over N. And then this one here, one of the S will cancel with this S. And one of the N here will cancel with this N, and so forth. So beyond the first term, you will always get terms with S and N in them. S in the numerator, N in the denominator. So every term here and beyond the 1, the denominator here will tend to infinity because N approaching infinity. So all these values here, this one, and beyond will approach 0, right? Since N tending to infinity. So you see, you'll just get 1 here. So that is why the delta Dirac function is just e to the minus S T naught. So what you have to do, you have to take the limit, right, of f n t as n approaches infinity in order to show that the delta Dirac function, the Laplace of it, is e to the minus S T naught. Right. So any questions on that so far? Right. So let me just stop there for a short while. Pause for a short while to see if everybody kind of okay on that. Okay, so let's move on here now, right? So we're looking at the differential equation. So we went through a number of examples with differential equations involving other types of function, piecewise function, where you're breaking it up into the Heaviside function. And we know how to apply the Laplace to a differential equation. So basically here we have a differential equation, you know, second order, equal to the delta Dirac function here, delta t minus 1. So your t naught here is basically replaced by 1, right? So think about that, subject to the initial conditions, right? Y naught is 0, right? And then y prime naught is 0. So we taking the Laplace here on both sides of the equation. So you take the Laplace of y double prime plus 9y, and then you take the Laplace of the delta Dirac function, right? So remember the Laplace of the delta Dirac function is e to the minus S T naught. So your T naught here is 1, so that will be e to the minus S, right? So that is the first thing you could do there. That basically straightforward. The Laplace of y double prime is S squared Ly minus S y naught minus y prime naught. And then the Laplace of y plus 9, the Laplace of y is just 9 the Laplace of y. And you have that e to the minus S, right? And then you substitute your initial condition, right? So y naught is 0, y prime naught is 0. So you're seeing it here. So this here I put 0 because this will drop out. So these two terms here will just drop out, right? So you'll have S squared, the Laplace of y plus 9, the Laplace of y, look at here, is equal to e to the minus S, right? So the Laplace of y is a common factor. So you have S squared plus 9 is equal to e to the minus s. So the Laplace of y is e to the minus s over s squared plus 9. And then to solve it now is to take the Laplace inverse, right? So yt is the Laplace inverse of e to the minus s, right? And remember this here will be 1 over s squared plus 9. And we know the inverse of that, right? So this here could be written as, right, 1 over 3 by 3 over s squared plus 9. Because the 3 will cancel. The 3 here on top and below here will cancel. And this is essentially, what is the Laplace of this? The Laplace of this here is sine 3t, right? So you see how they break it up here, right? So now when you're taking the Laplace of a exponential to some t naught s with some other function here, right? You're applying that rule there, right? So that will be, you pull the 1/3 on the outside. That will be the heavy side at t minus 1. And then it will be the function which is sine t, sine 3t rather, right? But you'll have to cater for the t minus 1. So you have sine 3t minus 1, right? So that is how you get this result here. Right, so you remember this. This is a very important formula here to remember here. One can associate a physical interpretation of the above example, right? The differential equation. So let's revisit this differential equation once more. Second order y double prime plus 9y is equal to the delta Dirac t minus t naught and t minus 1 rather. It models the undamped oscillation of a mass loaded on a spring where yt is the displacement from the equilibrium position at time t. Right, so look at it here, showing here on a diagram, right? So basically this spring, the object there hanging. So the object in equilibrium, right? But if some impulse is acted on the object here, it could move up, right? So it could move up from here to here as they shown in the arrow here, right? And that will create a displacement, right? And then when it moves up there, it might come back down again eventually, right? The right-hand side of delta t minus 1 of the differential equation may be interpreted as an upward unit impulse that is applied instantaneously at time equal 1. So when time is like 1 second, you have this impulse occurring, this unit impulse, right? The initial condition, right? So it means that the initial, initially the distance is 0, so y naught is 0, and then the initial velocity is 0 as well, right? So y prime 0 is 0. So that implies that the mass is at the equilibrium position and at rest at time t equals 0. So if it at rest, it means that the distance is 0 and the velocity is also 0. Hence the initial conditions, right? So these are the two initial conditions. So the delta Dirac at t minus 1 here is equal to 0. When t is not equal to 1, we have that the second order differential equation is equal to 0. When t is equal to 0, and therefore we replace the t here in the equation by 0. So we have y double prime 0 plus 9y0 equal to 0. And we know that this here would imply that the acceleration is also 0. So since the displacement is 0, right? In addition to being at rest, at the equilibrium position, the mass is not accelerating at time 0 as well. So the mass is therefore stationary and does not move from the equilibrium position until a unit impulse is applied at time t equal 1. The mass then begins to oscillate freely without damping about the equilibrium position, as can be seen from the graph of the solution, right? So, I mean, we could graph this here, seeing it here at third. So you remember the Heaviside function here, right? So it's at third h at t minus 1. So up to 1 here is at 0, right? And then after it reached 1, it started moving a sine formation, a sine graph. You understand? So you have a oscillation wave going up and down between 1/3 and negative 1/3. Right. So that is the Dirac delta function here. Right. So that is the theory behind it. Right. So you must be kind of, familiar with intuitively what it stands for, right? Periodic function. So I mean, we know what periodic functions are, right? I don't know if you encountered it already, right? So let's look at the definition here. Let ft be a function that is defined for all t. Then ft is called periodic if there exists a positive number such that f at t plus capital T is equal to f at t, right? So that is what periodic means. So whatever the function is at some parameter plus another parameter, it will be equal to the function at the initial parameter then for each t. So if this was a p then, right, and you get the same thing, it means that the function is periodic with parameter p, right? So here now, the number t is called the period of the function. So if it had p here, the p would be called the period of the function. Show that f of t equals sine t is periodic with a period of t equal 2 pi, right? So by definition here, we go replace capital T by 2 pi. So therefore, we must show that, the function here is a sine function. So sine t plus 2 pi would be equal to sine t. So let's use a trigonometric addition formula. So this is straightforward. Sine t, right? So this is sine A plus B. The sine A cos B. Right? And then you add in cos A sine B. So all we do is we substitute t for small t for A and 2 pi for B. So you see here, you will get sine t plus cos 2 pi. Sorry, sine t cos multiplied by cos 2 pi plus cos t, right? So it's just written in reverse here, right? So plus cos t right, by sine B, and sine B is 2 pi, right? So it's just written in reverse. Now, sine t, we don't know what that is, but we know that cos 2 pi. So cos 2 pi is 1, right? And sine, any multiplier pi on with sine is 0. So therefore, this part here just will fall out. So you just get sine t by 1, which is sine t. So you see you get sine t plus 2 pi, giving you back sine t. So therefore, this function is periodic, right? And the period here is 2 pi. Basically, what I'm telling you, it means between 0 and 2 pi, the function have a certain graph, right? And then every interval beyond 2 pi, every interval less than 2 pi, you will have a repeat of that graph formation then, right? And you will see just now in some of the diagram. So look at the square wave, right? So the square wave here, piecewise defined, look at here, 1 between 0 and 1, and 0 between 1 and 2, right? So this function here is periodic, and the period here is 2. So basically 2 means the distance between 0 and 2 is 2, right? So if you look at the t-axis here, this is 0 here, and this is 2 here, right? So between 0 and 2, what's happening? Between 0 and 1, the function is defined to be 1. That is this horizontal line here. But remember, you have a bold circle here by 0 because it includes 0, and an open circle here at 1 because it doesn't include 1. Then between 1 and 2, inclusive of 1, the function is 0. So it's gone back down on the t-axis. So you have a bold circle on the left side of the line, and an open circle here, but because it doesn't include 2, right? So what would happen is between 2 and 4, the same thing will happen because that is another period, right? Between 0 and -2, the same thing would happen. This is -1 here, and this is -2. So every distance at 2, beyond 2, or less than 2, every distance, right? Every distance at 2, then you will have this, you'll have a repeater what you saw there between 0 and 2. So you see between 2 and 4 here is the same. Watch out this line here between 2 and 4, and this line on the t-axis, and the line above where ft is 1, and look at here on the t-axis here, and you could continue the process, right? So all you have to do is draw the graph for one period, and then you could just, you know, continue for another period, more than or less than, right? So no, a lot of times in exams, you might be given a periodic function, and you might see to sketch the periodic function for at least 2 periods, right? So when I say at least 2 periods, this is just one period here, right? So you gotta sketch it for, that is one period, and then this is another period here. So that would be at least 2. At least 2 will be 2 or more, right? And if you do a third one, no harm in that, because 3 is more than 2, right? So you have an understanding of the periodic functions, right? How to graph them. Any questions on that? Okay. So we have a rectified sine wave here. So your sine wave here now is like it compressed between 0 and pi. So your period now is pi. So the period get cut down, right? Up here, your period was 2 pi, right? Down here, period is pi. So what would happen here? So between 0 and pi, you have your sine t. So your sine t is this shape here. Then. So that is one period here. Right? So if you had to repeat that, then you had to draw the same hump again between pi and 2 pi. And then you could draw it between 0 and minus pi. You could go between 2 pi and 3 pi if you wish. Right? But this is more than 2 periods here. Right? So normally in exams, they ask at least 2 periods. Right? So now we come to a very important theorem here. Right? So if ft is periodic with period t, then the Laplace of ft is equal to the integral between the period and 0 e to the minus st ft dt divided by 1 minus e to the minus s capital T, which is the period. Right? So this is a theorem here, and this is equivalent to the Laplace of ft is the Laplace of 1 minus the heavy side of t minus the period by ft over 1 minus e to the minus st. So this part on top here is the Laplace of 1 minus the heavy side t minus the period multiplied by ft. So let's look at the proof here of this here now. Right? So in order to prove this here, we go back to the basic definition of the Laplace transform. Right? So you remember the Laplace transform, L of ft, is the integral, right? The integral between infinity and 0, e to the minus st by your function, f of t dt. Right? But remember, this function is periodic, so you have to break it up into t and 0. So you're taking the integral between t and 0, which is your period, e to the minus st ft dt. And then you're taking you're adding it to the integral between infinity and t, e to the minus st ft dt. Right? So what happening here now? This here, notice these functions here on the right, this one in particular. You're integrating here, you're integrating, right, a function in terms of small t, but you're taking limits here with infinity and big T. So what you have to do here, you have to make a change of variable here then to accommodate for this big T, right? So what you say here, apply a substitution, let u equal t minus big T, small t minus big T. So what would happen here? So if u is small t minus big T, what small t will be? U plus big T. See now there? Right? You carry the T across, right? And so you replace this here on top here, this T by minus S into U plus T, and F into U plus T du. So your variable is in terms of U now, right? And what would happen here with the limits now, right? The limits will change from infinity to T, sorry, between infinity and T to infinity and 0. Why is that? Right? Because remember here now, using this substitution, and if your T here, because remember this is in terms of small t, if your T is replaced by big T, what will happen? That would be t minus t is 0. So that is why it has 0 here. So your limits now would be infinity and 0 now in here now, right? And here now you're gonna be really integrating here with respect to u. So it means that this t here you could take that on the outside. So this is really e to the minus su minus st. So you could pull out the e to the minus st on the outside. We could have nothing to do with the integral. The integral is with respect to u. The integral between infinity and 0, e to the minus su. And then this here, remember, the function is periodic, right? And the period is t. So the u plus t becomes just f of u. That is because of the fact that it's periodic. You see, look at it written here. So now we have the limit between t and 0, e to the minus st ft dt plus e to the minus s to your period t. The integral between infinity and 0, e to the minus su fu du. And you remember this u here is like a dummy variable, so you could go back to small t, right? So you see it's written here, e to the minus s capital T, e to the minus s small t ft dt. So initially it was a dummy variable. So this is what you get here now. And the part on the left remains, right? So now your Laplace transform of ft is really the integral between t, capital T and 0, e to the minus st, ft dt, which is your integral on your left, and your integral on your right now, right, is e to the minus st. And you remember this integral here, by definition, is really the Laplace, right? Is really the Laplace of ft. Right? So you have your Laplace of ft. You could put all your Laplace of ft's on one side of the equation. So this here you carry it across, right? So when you carry this across, you'll get minus e to the minus st L ft. So you could pull out the L ft, so you get 1 minus e to the minus st. The integral between capital T and 0, e to the minus st ft dt. And then the Laplace of ft would be just this integral divided by 1 over e to the minus st. And that is what you require. Note that the 1 minus the heavy side t minus capital T in bracket by ft, where ft is defined to be ft between 0 and t, right? And then 0 otherwise. Anything greater than t or equal to t will be 0. You can remember here now, if you're breaking up this into the heavy side, you gotta take 1 minus h at t minus t, the two endpoints, and multiply it by ft. And then this one here will be, the second one will be h t minus t by 0. So the second part won't have any contribution. So the Laplace transform of 1 minus h at t minus your period by ft is the integral between capital T and 0, e to the minus st ft dt, plus the integral between infinity and t, e to the minus s t by 0. Because in this region here, it defined to be 0. This region here defined to be ft. So this part here obviously will drop out. So you will just get this here. So we may write this here over 1 minus e to the minus st is the Laplace of ft. which is the alternate way of writing it, right? So you just replace the top part here by this. And this was how to show you there, right? So you replace that part there by sawtooth wave. Let ft equal t and t between 0 and 1. And we say that the function here is periodic with period 1, right? Meaning that between 0 and 1, you have the function to be t. So look at here, between 0 and 1 is t. And then between 1 and 2, you'll get the same thing occurring. Between 2 and 3, you'll get the same thing occurring. Between minus 1 and 1, you'll get the same thing occurring. So this is periodic here. So we have 4 periods here sketch. And now you have to find the Laplace. So by this formula here, the Laplace, open brackets 1 minus ht minus 1 ft over 1 minus e to the minus s t. So we could work out this here now. Remember what t was, right? Ft is t. So let's work out the top part first. So we have 1 minus the heavy side at t minus 1 multiplied by ft. So you replace ft by t, right? And then you see you're multiplying t by 1, and then you're multiplying t by minus h t minus 1. And we already went through several examples with this here. So this tends to occur a lot, right? So this here could be written as h at t minus 1 bracket, right? You could break up this using the distributive property. T minus 1 plus 1. So this is going to be minus h at t minus 1 by t minus 1. And then you'll get, so look at here. And then you'll get minus h at t minus 1 by 1, which is minus h at t minus 1. Right? So anytime you're doing the Laplace of a heavy side, you have to expand it out in that way in order to evaluate it. And now you have to take the Laplace at t, the Laplace at this middle part here, h t minus 1, t minus 1. You know why you have to expand it? Because you can't really find the Laplace t by h t minus 1. There's no rule to do that then. So you have to break up this into h at t minus 1 by t minus 1. You could do that. And then you'll get minus h at just t minus 1. You could do that. So whatever the heavy side, whatever is your t naught in your heavy side, your function must have that in it as well. So you take the Laplace of the 3 terms here now. And of course, the Laplace of t is 1 over s squared. The Laplace of h t minus 1 into t minus 1 is e to the minus t naught by s. And your t naught here is 1, so that is e to the minus s over s squared. And the Laplace of h at t minus 1 is e to the minus s over s. And you have a negative here and a negative here, and the negative and negative in the second and third term. So your signs are important when you're doing your problem solving. You have to be careful with your signs. Make sure you take care when dealing with these things here. So your numerator here is replaced by 1 over s squared minus e to the minus s over s squared minus e to the s over s. Right? So this could be simplified, right? So you into 1 minus e to the minus s into 1 plus s all over S squared 1 minus e to the minus s. Right, so if you want, you know, we could do that step here. Right, so we have S squared. Make S squared your LCM in your numerator. So what you get? You get 1 minus e to the minus s. Because the first two terms here have S squared as your denominator. But then this one here, the third term you have is you have to multiply it by S. So that is S e to the minus f. Right? So this will become 1 minus e to the minus s minus s e minus s over s squared one minus e to the minus, sorry, yeah, 1 minus e to the minus s. And what are the numerator here? E to the minus s common in the second and third term. So you could pull out e to the minus s, and then you'll end up with 1 plus s, because our minus outside here by plus will give you back your minus. So that is how I get this across here, right? Right, so this was the periodic functions here. Poles and zeros. Right. A system is a mapping H that assigns a unique output YT to an input UT. It is customary to represent a system as a black box with the input and an output. So you see, look at the diagram there showing the input is your function UT, your output is your function YT, and you have your box there, your system, right? So when it go through there, you end up with some process and you end up with your output coming out YT. Right, so these are examples here of system here, right? Consider the following LR series circuit, right? So you have here your input voltage UT and your output current IT. This is an example of a voltage as your input and a current as the output, for which the input in the voltage and the output of interest is the current. Using Kirchhoff's voltage law, we have this system is modeled by this differential equation here, right? This first order differential equation, L di over dt plus IR is equal to UT. Consider again the LR circuit where this, in this case, the output of interest is the inductor voltage. So look, the output here is the inductor voltage. The input is the voltage, right? And instead of current this time as was in the previous case, right? Here is the output here is the inductor voltage, denoted by VLT, right? So here we have here L d I over dt plus IR is equal to UT. And by definition of inductor voltage, we have the L di dt equal to VLT. So differentiating 21 and 22 with respect to t gives. So 21 and 22 here you differentiate. So what will happen to the first order? It will become a second order. What will happen to this term here? You'll get di dt here. And then on the right hand side, you'll get u prime t. And then you replace here now the second order L d squared I over dt squared by VL prime t, right? So I just writing this extra that VL prime t plus R over L VLT is equal to U prime t. So here now you're replacing the current here by the inductor voltage. You see it here? And this models the LR circuit system with input UT and output VLT. Consider a system modeled by the following differential equation, right? So you have a constant here, A naught y to the nth derivative of t plus another constant calling it A1 y to the n minus 1 derivative of t. All right, so you notice your constant and them going up and your derivatives coming down. So then you end up with n minus 1 y to the first derivative, t, right? So notice something. An easy way to see this is like the difference between the subscript in your constant and your derivative, your nth derivative is always 0 n, right? So if you notice n minus 0 is equal to n. This is an easy way to see them. And then n minus 1 rather you're adding it and not subtracting it. So the order of the derivative here and this subscript here must always add up to n. So what you see here, n minus 1 and 1, you'll add up to n. And then if the subscript here is n minus 1 and the derivative here is 1, so you notice the n minus 1 and 1 will cancel and you'll get n again. And then n here, this will be the no derivative at all. So this is like, you know, not really 0, but no derivative. You understand? Right? So this is equal to b0 x to the m t plus b1 x to the m minus 1 t. So this is the part on the left hand side of the equation. This is the part on the right hand side of the equation, which is similar. It's just a different function. Now this is a function of y at t, and this is x at t, right? b1 x to the m minus 1 derivative at t, bm minus 1 x to the first derivative at t plus bm x to the no derivative at t, just xt, where m is less than or equal to n. So that is very important. So this power here, or this derivative rather, m can exceed n. M could be less than n, right? And it could be as large as n, but it can't be greater, right? So check what happening here. The transfer function is hs of this system is defined as, right? So what should happen here? So what kind of fraction you'll have here? if you look at what they're telling you about there, these derivatives here will be in the numerator, and these derivatives here will be in the denominator, right? So you could never have your denominator, right, will always be less than or equal to your numerator in terms of the derivative. And this is the ratio of the Laplace transform of the output to the Laplace transform xs of the input, xt, under the assumption that all initial conditions for xt and yt are 0. So by taking the Laplace transform and inserting the 0 initial conditions we have, right? We have ys a naught s to the n plus a1 s to the n minus 1 and so on ans an is equal to x of s b naught s to the m plus b1 x s to the m minus 1 plus b m minus 1 s plus bm, right? So notice now this here, because we cross multiplying, right? So this part here, we take out the ys then, because we take the Laplace of the whole part on the left, and we take the Laplace of the whole part on the right. So you pull out ys here, and then you have all these terms added. And then you pull out xs, and you have all these terms added on the right. And then the transfer function is ys over xs, right? So see how what will occur here. Ys over xs, you'll end up with this one on top and this one underneath when you cross multiply. So it means that the Sn, the powers in the denominator, will actually be higher than the powers in the numerator. Or the most it could be is equal to each other. For the LR series system, the input voltage and you have the output current here. The same system that was described earlier, L di dt plus R it is equal to ut. So let's look at the transfer function here now. Right, so you're taking the Laplace. You're taking the Laplace of di dt, the Laplace it, and the Laplace ut. So the transfer function is obtained by taking the Laplace at 26 and using the initial condition. So the initial current is 0, right? So you have remember this is our first order, right? So this is like y prime, right? So recall if you take the Laplace of our first order, that will be sys minus y naught. Right? So that is S, but it's not ys here, it's is, because it's current. So your y replaced by I, so you see sis minus I naught. That is the initial condition. And then your Laplace transform of rit. You pull the r on the outside and you have is, and then your Laplace ut will be us. Right? And then these two terms on the left, you could factor the is. So you'll get SL plus R is equal to US. So IS over US, so this one comes underneath here in the denominator position. So therefore this will go down here in the denominator position. So IS over US is 1 over SL plus R. And that will define the transfer function HS, IS over US, is equal to 1 over SL plus R. So for the LR series system with output of inductor voltage, VLT, right? So we're going from current now to inductor voltage. That was the other case. We have the input voltage, UT, and the output voltage here by VLT. Right? So the same thing apply here. If you take the transfer function here now, right? You're taking S VLS minus VL of 0, R over L VLS, and then you're taking the first derivative of this here, so that is SUS minus U naught. And then you insert your initial condition, so this term here will come out, and this term here will come out. So you end up with S VLS plus R over S VL S is equal to SUS. So which, if you factor out the VLS here, you'll get in brackets here, S plus R over L is equal to SUS. And therefore VL S over US would be S over S plus R over L. Right, so basically this will come down on the left in the denominator position, and the US will come in underneath here on the, this will come on the right here in the denominator position, and the US will come on the left here in the denominator position. So you'll get the S over S plus R over L. And so the required transfer function, when you're talking about the function involving the voltage, right? The output voltage is VLS over US is S over S plus R over L. Right, so the definition here now is the transfer function of a system may be written as the ratio of the polynomials with real coefficients in the S variable. So take that into consideration, right? It would be written as a ratio of polynomials with real coefficients in the variable S, where PS and QS have no common factors. By factoring both PS and QS into linear factors, we may write HS is equal to PS over QS is equal to K into S minus W1 to the power M1 into S minus W2 into to the power M2 and so on, S minus WK to the MK, all divided by S minus Z1 to the N1, S minus Z1, Z2 to the N2 and so on, all the way up to S minus Zi to the Ni, where these values here in the denominator, the complex values, Z1, Z2, and so on, Zi are called the poles, right? So what is saying here, when written in this form here, the transfer function, right? And you have all these linear factors here in the denominator. Whatever value would make a linear factor 0, right? is called a pole, right? So if 0 mean whatever value is substituting here, in order for this to be 0 here, this factor to work out as 0. And the power of the factor is called the order or multiplicity of the pole, right? So this first pole here has order n1. Well, this first factor here has order n1. We don't know the polars here. The pole is what will make it 0. Right? And the order is also called the multiplicity. So if the order, the pole is 1, the multiplicity is 1, right? The multiplicity is 1, we call it a simple pole, right? If the order is 2, we call it a double pole. So if the power is 2, we call it a double pole, and so forth, a triple pole, right? And so on. And then the values in the numerator now that will make these factors here 0, right? They are called the zeros, right? Of the system, where the order of the zeros is the positive integer m. So the power will denote the order of the zeros. And this real number here that you have as a factor on the outside of the numerator, we call it the gain of the system. A pole zero plot is a diagram indicating the location of the poles and zeros of a transfer function on the complex S-plane. The location of a zero is marked by a small circle, and the location of a pole is marked by a cross. Right? So you must be very clear on your notation, right? Because if you mix up x as if you mix up a 0 as a x and a pole as a 0, you wouldn't get that correct, right? In your mind, you might be seeing it correct, but it's something standard. You must maintain the correct notation. So that is why it's so important when you're doing these things. You have to be careful and to keep to the notation that that is given in the course then, right? The multiplicity, if greater than 1 of a pole or 0, is written next to its corresponding symbol. Right? So a system is modeled by the differential equation. Right? So this here, y double prime t plus 2y prime t plus 5yt is equal to 3u prime t plus 12ut. So where ut and yt are respectively the input and output of the system. So remember, the u is the input and the y is the output. Find the transfer function of the system, determine the poles and zeros, and draw the pole zero plot of the system. Right? So basically, you take the Laplace transform and then you put all your initial conditions at 0. So anytime you're finding the transfer function, you're basically taking the Laplace transform on both sides of the equation and you're setting all the initial conditions at 0. So you see u naught is 0, y naught is 0, and y prime naught is 0. So you end up here, when you take the Laplace of y double prime, you'll get s squared ys plus right, so remember you'll get s squared ys minus s y naught minus y prime naught. Right? And then for the next one here, if you take that there, you'll get what? You'll get 2s minus y naught. And this one here, on the right hand side, you'll get 3 right? I forgot to multiply by the 2. So I don't multiply this by 2. But I mean, as you would see, it will drop over because your initial condition is 0. And then for the right hand side here, you'll get 3 s us minus 3 u0. And then finally, right, so the Laplace of this term here is just 5ys. And the Laplace of this one here is 12. Because these two terms here, the last one here on the left and the last one on the right, have no derivative in them. So that is just your t variable changing to s then. So that is important. Right, so remember what's happening here. This will be 0, this will be 0. So all will survive is this, right? And then the second term here, this part will be 0 because your initial condition is 0. So all that will survive is this. So you'll end up getting s squared ys plus this term here, 2sys plus this term here, that is the last term, that is the term that we had up here, look at here. And then the second one, you'll get 3s us, and this will be 0 because all your initial conditions are 0, plus the 12 us. You see that there? The Laplace at 12 ut. So we could factor the ys here now, and you'll get s squared plus 2s plus 5. You factor the us here, you get 3s plus 12, and then ys divided by us. So it will be 3s plus 12 divided by s squared plus 2s plus 5. So you notice the numerator here now, the power s is less than the power in the denominator. And this is your transfer function, right? Now if you factor the numerator and the denominator, right? So you remember 3 could be a factor here. So this could be like your k then. And then if you look at the denominator here, this is s plus 1 squared, right? Plus 4. S plus 1 squared plus 4. So now this part here, you could break it up into, right? You could break up this here because this could be s plus 1 squared plus 2 squared. And by looking at that there, we see that the denominator is the sum of 2 squares, right? Which will factor out into s plus 1, that is the first term, minus 2i, s plus 1 the second term, minus 2J. Right, so this here is complex, right? So the numerator here, you have 3 into S minus minus 4. And the denominator, you could further break up this into S minus minus 1 minus 2J. And S minus minus 1 minus 2J. So you get back what you had originally. Look at it here, right? So this here will define your pole. So the system has a 0, right? Your 0 here is minus 4 because the 0 is on top. If you put minus 4 here, you're seeing minus 4 plus 4 is 0. So your numerator here will be 0. So that is why minus 4 is a 0. That is why we write it in this form here. And if you put S equal in the denominator here to be minus 1 minus 2J, this will be 0. And similarly on this side, if you put minus 1 plus 2J, this will be 0. So you'll get a pole here and a pole here, and the pole, the order of both poles are 1, right? So both of them are simple poles, right? So now you want to sketch this here on the on the S plane, right? So your poles and your zeros on the S plane. So you have your imaginary axis, IMS, your real axis, right? And the first thing to remember, what do we, the 0 is a O, and the pole is a X, right? So your poles lying minus 1 minus 2J. So you have your 2J here, this is the imaginary axis, and your 2J down here, and you have your minus 1 to the left. So this is where your poles will lie, right? In this position, an X here and an X here. And the 0 will lie by minus 4. That is on the real axis here, the real S. Right? So I want you to look at that carefully. So now, next day when we come, we're gonna look at more transfer functions and how good to go about them and write them. If you give me a differential equation, right? With an input and an output functions, how to write the transfer function and how to find the poles and zeros and how to sketch it on the S plane, right? So let me just come out of the share here. So any questions on that so far? Right, so I want you to revisit all that and go through it carefully, because sometimes the problem does be not the understanding of the theory, but the practicing, right? So if you're going to finance, you will be able to see some problems of that form where you're writing a differential equation, you're writing the transfer function. And so look at some of those exercises, because sometimes when you're dealing with a particular differential equation, it might be of maybe a third order or something, and some people might have problems factorizing it. So you have to practice a lot of the different types in order to get the feel for it, right? So let me reiterate again that the exam, the midterm is on the 8th, right? It's on the 8th between 1 and 3, which is Friday the 8th, right? And the format is as last semester, same type of question, multiple choice, numeric responses are mixed here, right? So you make sure you continue with your preparations, right? I went through quite a lot of problems in preparation for that midterm exam, and now we're going to be looking at more problems for like your beyond the midterm exam, the delta Dirac function and the periodic functions and so on, and transfer functions and poles and zeros and all these things, and sketching the diagram. Right, so next day when we come, we'll continue. Anybody have any questions? No questions? Right. So if you don't have any questions, we could end here, right? And we'll continue next day, Wednesday, right? So I will see you then. Take care. Right. Okay, bye.